significantly change the properties of the physical system we're talking about. So that's why we should take care of the open quantum system and the corresponding physics in there. So the physics states in the open quantum system should be mixed state rather than the pure state we're talking about for the previous study. There are several concrete examples for the mixed states. The one of the example is the quantum error correction codes. One of the motivation of introducing the quantum error correction codes is that during the transmission of the quantum information, we should take account of the noise and their impacts of the quantum information. You know that to avoid the corruption of the quantum information, we should introduce more ancillary qubits and the corresponding algorithm to do the error correction. So the sensitivity and the robustness against the external noise of the quantum error correction code is pretty important and aka the decodability of the quantum error correction codes is one of the central issue for the quantum error correction problem. And the second motivation of investigating the mixed state is that during the past few years, the development of measurement-based preparation of the quantum states is pretty exciting. And in this setup, for example, in trapped ion quantum computer, etc., the interaction between the system and the environment is inevitable because you do perform the measurement. And the measurement will introduce the interactions between the system and cell. So it's pretty important. All this kind of example shows the importance of the investigation of the mixed quantum states. And mixed states in open quantum systems are usually described by the density matrix rather than the pure state. Okay? Before we're talking about the mixed state as the corresponding equivalence relation. Well, the equivalence relation of talking about the physical matters, one of the most important thing should be defined. So before we talk about the equivalence for mixed states, let's review the equivalence relation for pure states. The equivalence relation of different pure states can be defined based on the quasi-local unitary evolution, aka a time evolution operator of the Hamiltonian dynamics. And we say two quantum states, psi1 and psi2, both of them are pure states, are equivalent in the sense that we can find a local unitary, quasi-local unitary operator, or we can find a Hamiltonian, corresponding Hamiltonian such that the corresponding time evolution operator can relate psi1 to psi2. And one of the very elegant property of the unitary operator is that if we can find one-way connection between psi1 and psi2, let's say psi1 equals to u psi2, then we can automatically find the reverse way to deform the psi2 back to psi1. Just apply the U dagger to both sides of the equation. We can easily to show that we can deform psi2 back to psi1 by U dagger. And based on the equivalence relation between different mixed pure states, we can draw such kind of phase diagram. And every single pair of states within the same phase in the phase diagram can be related by a unitary operator in a two-way sense. For more details, you can refer to the paper written by Hastings and Xiaogang Wen in 2005. Okay. And things become completely different for the mixed state in the sense that for the mixed state, we can never describe the evolution of the quantum states by a unitary operator. Because as I said before, one of the key difference between open quantum system and closed quantum system is that it's the interactions between the system and the environment. So before we talk about the equivalence relation, we should define the dynamics in the open quantum system. The most generic way of describing the dynamics in open quantum system is actually the local quantum channel rather than the unitary evolution. So we should first give the formal definition of the local quantum channel. There are three main steps of applying a local quantum channel that deform the density matrix rho to E rho as an initial and final states. The first step of the quantum channel is that, well, as I said before, the quantum channel just described the evolution of rho that encounters the system and the environment's coupling. So the first step is that we just include all the ancillary degrees of freedom towards a enlarged Hilbert space. This enlarged Hilbert space includes both the system we are talking about and the environment that is included in the coupling. And the second step is that well, right now we have an enlarged Hilbert space, and the enlarged Hilbert space, including the system and environment, is an enlarged closed quantum system. So in this enlarged closed quantum system, we can actually apply the local unitary operator to describe the dynamics in the enlarged Hilbert space. And then because we are only care about the physics in the physical Hilbert space and the system, AKA we don't care about the dynamics of the environment. So then the final step of defining a quantum channel is that we trace out the ancillary degrees of freedom. These three main steps, it gives some formal definition of a local quantum channel that generate the dynamics in the open quantum system in the most generic way. Okay, after defining the formal definition of local quantum channel, I'm going to tell you a drastic thing about local quantum channel compared with the local unitary operator is that for quantum channel, which is generally non-unitary, the elegant property of two-wayness of the unitary operator is no longer appear. For example, for people, you guys just wake up and come to the office and work, and after work you come back to your home apartment. It's actually two-way connectivity. But if somebody suicide, it's not a reversible process. It's only a one-way connectivity. So unfortunately, where the quantum channel is not if two density matrices can be one-way connected by a quantum channel, it's not necessarily to have another channel to drive the final state back to the original state. Let me show you a very extreme example. Is that every single mixed state is one-way connected to a product state by a local quantum channel. Let me show you why is that. Let's consider a density matrix rho and an ancillary degrees of freedom which has been put in the product state. So we just apply a swap gate in large Hilbert space that basically exchange the degrees of freedom in the physical and the ancillary Hilbert spaces, and then we trace out the ancillary. So by our formal definition, the process I'm talking about is a legitimated local quantum channel, and this channel are going to destroy every single mixed state to a product state in the sense of local dynamics. So to define a phase of matter in open quantum system, the two-way connectivity is essential in the sense that if we say the two density matrices rho 1 and rho 2 are in the same phase, we should find we should find two different quantum channels that deform rho 1 to rho 2 by one way, and another channel that deform rho 2 to rho 1 back to rho 1. That's the sufficient and necessary condition of defining a equivalence relation in open quantum system between different mixed states. Okay. After talking about the equivalence relation of different mixed quantum states, let's define the symmetry of the quantum state as one of the most important property of the quantum states. The symmetry is pretty powerful for both pure state and thermal states. So for pure state, the symmetry is pretty simple to be defined in the sense that if we say a pure state psi is symmetric under some symmetry G, it actually means that we have a linear representation of the symmetry group G in the Hilbert space. Let's see, for the group element little g, we have the representation UG as a unitary operator or anti-unitary operator in the Hilbert space, and then we apply this operator on the pure state we're talking about, and this pure state remain invariant up to a global phase because the quantum mechanics tell you the global phase is not that important. So that's the formal definition of the symmetry for pure states. But for mixed state, things become completely different. First of all, there are two different classes of the symmetries in open quantum system. The first one is the strong symmetry, aka exact symmetry. The meaning of strong symmetry is that if we only apply a symmetry operator in a specific side of the density matrix, the density matrix is invariant up to a global phase. The second class of the symmetry is a weak symmetry. And the weak symmetry demands that if we only apply the symmetry operator on a specific side of the density matrix, the density matrix is not necessarily invariant under this kind of action. But if we conjugate the symmetry operator to the density matrix, that is applied in both sides, the density matrix is actually invariant. You can recognize that the strong symmetry is a stronger condition than the weak symmetry. But what I said is a little bit abstract. Let me show you another interpretation in terms of a language that the condensed matter physicists are more familiar with. Let's consider a specific basis of the density matrix, and then we are talking about an ensemble of states. The strong symmetry demands that every single state within this ensemble should be symmetric under this symmetry with the same symmetry eigenvalue. It's a pretty strong condition, right? And for the weak symmetry, every single state within the ensemble is not necessarily to be invariant under the weak symmetry operator, but the rule of the weak symmetry operator is only repermutation within the ensemble. It seems that we can transfer different states, transfer between the different states by the weak symmetry operator, but all the states we're talking about should be included within the ensemble. And if we try to diagonalize the ensemble under the basis of weak symmetry, we can see that we can achieve that every single state could be symmetric under weak symmetry, but the symmetry eigenvalue could be different. That's the key difference between the strong symmetry and the weak symmetry in the sense of the ensemble of states. Okay, by defining the equivalence and symmetry in the open quantum systems, let's review the concept of spontaneous symmetry breaking. Firstly, in the traditional sense, as the one of the organizing principle in the modern condensed matter physics. For example, we're pretty familiar with the paramagnetic to ferromagnetic phase transition in the magnetic systems. For the paramagnetic states, the order parameter that is a local magnetization is vanish, and for the ferromagnetic phase, the local order parameter that is the magnetization is non-vanishing. It's pretty easy to be experimentally proved. Okay, and an alternative way of defining the spontaneous symmetry breaking is in the sense of the quantum state. Let's consider a 1D qubit chain with a strong Z2 symmetry. The symmetry generator is actually the product of poly X operator. Let's consider the GHZ state, which is also called the CAS state, as the quantum superposition of all up and all down quantum states. There are several key important properties of such kind of CAS state, which is obviously a spontaneous symmetry breaking of the Z2 Ising symmetry. The first important property is that the CAS state has a long-range order of the poly Z operator. You know, the poly Z operator carries the non-trivial charge of the Ising Z2 symmetry in the sense that the poly Z operator is not commute with the symmetry generator that is a product of X. And the other property is that the psi plus minus is non-invertible, in the sense that we can never find another pure state that, let's call it psi-total, and a strongly symmetric unitary U such that we can deform psi tensor psi-total to a product state through U. It's not possible at all. So that's the key properties of the spontaneous symmetry breaking on the level of states. Okay, during the past half of decades, the understanding of spontaneous symmetry breaking has established in terms of the Ginsburg-Landau paradigm. For example, the classical Ginsburg-Landau paradigm described the SSB in the thermodynamic system. That described the SSB from the weak symmetry to no symmetry. On the other hand, the quantum Ginsburg-Landau theory established the theory of the quantum phase transition of the spontaneous symmetry breaking that breaks the strong symmetry to no symmetry. So as I said before, there different kinds of symmetries that is strong symmetry and weak symmetry. So you may ask me a question: if there is any phenomena that breaks the strong symmetry to weak symmetry spontaneously for mixed state, yeah, here it is. Here is actually what I'm talking about in this talk. It's a strong to weak SSB. Okay. Another elegant property of the pure state SSB is the spontaneity, which is captured by its divergent susceptibility. Let's imagine the cascade again. You can see that the cascade seems like, oh, well, it's symmetric under Ising symmetry, but this symmetry property is so fragile that if we even in the thermodynamic limit, if we only apply a Zeeman, the external Zeeman field along the z direction only on one side is enough. Infinitesimal h. The symmetry property will be completely destroyed in the sense that the state gonna be collapsed to either all up or all down, depends on the sign of the h. And this certain change means that although the cascade is symmetric, this symmetric property is pretty fragile in the sense that a local perturbation can lead to global change of the whole system. And this spontaneity phenomenon can be captured by a divergent dynamical susceptibility. In this case, it's a magnetic susceptibility, which is defined as a derivative of the magnetization with respect to the external magnetic field. That's the formal definition of the magnetic susceptibility for the magnetic system. So the spontaneity is a very important property of the spontaneous symmetry breaking for pure states. Okay, for a very long time, almost 1 decade, we believe that the canonical ensemble and the grand canonical ensemble are locally equivalent, in the sense that for every single local observable, we can test the expectation value either in canonical ensemble or grand canonical ensemble, and it will give you the same answer. But from the symmetry perspective, there's very subtle difference between these two ensembles. For example, for the canonical ensemble, the corresponding density matrix is strongly symmetric in the sense that the particle number exchange between the system and environment in the canonical ensemble is not legitimated. But for the grand canonical ensemble, because at this time, the particle number exchange between the system and the environment is legitimated, so the corresponding density matrix of the grand canonical ensemble is only weakly symmetric. So our conjecture is that if a Gibbs canonical ensemble of a local Hamiltonian H, and this Hamiltonian does not have any spontaneous symmetry breaking, and then the corresponding Gibbs canonical ensemble must have a strong to weak SSB. That's our conjecture. But what the sense of the SWSSB, I will show you in the following part of my talk. Okay, after a very long introduction part, here's the outline of the main text of my talk. Maybe too long. Okay, and the main part of my talk includes two parts. The first part is the formal definition of a strong to weak SSB, including two very important, maybe the key properties of the spontaneous symmetry breaking to demand that it's a true mixed state, well-defined mixed state phase of matter, and it's actually a spontaneous symmetry breaking. The first one is reflected by the stability theorem, and the second one is reflected by the spontaneity theorem. And with the formal definition and the properties, I will show you a very simple example. That is a 2D quantum Ising model under symmetric decoherence, and you can see that there is a transition, quantum phase transition between the symmetric state to the strong to weak SSB. And I will show you what exactly the universality class is of the corresponding transition. And the second part of my today's talk is the fluctuation dissipation theorem in the open quantum system. Firstly, we define fidelity magnetization, fidelity susceptibility, and related the fidelity susceptibility to some kind of two-point correlation function, or it's actually a generalized two-point correlation function, not the traditional two-point correlator. And to establish the generalized fluctuation dissipation theorem that basically relates the dynamical properties of the system and the correlation correlation behavior of the system. Okay, and finally, we provide a experimental probe by the well, it's actually an estimation because the precise probe of the fidelity susceptibility is possible, but a reliable estimation is possible. And I will show you that by the classical shadow tomography, we can reliably estimate the fidelity susceptibility and estimate the corresponding phase diagram in the open quantum system. Okay, let's move to the formal definition of strong to weak SSB. Let's consider the 1D qubit chain again with the Z2 Ising symmetry. Let's consider such kind of density matrix that is 1 plus product of X. This symmetry looks pretty simple in the sense that this density matrix is strongly symmetric. Let me show you why is that. Let's apply the product X. For example, act on the left-hand side of the density matrix, and then the final density matrix still 1 plus X. It's pretty simple. And this density matrix can be easily to prepare from a product state by just step 1 quantum channel. This quantum channel is the nearest neighbor ZZ defacing. The cross operator representation of this channel is on the bottom line of this slice. That is, let me show you. It's a ZZ defacing channel. It's actually the nearest neighbor ZZ, and you can prove that under this channel we can actually deform a product state to a to the E1 plus X state we're talking about. So you may ask me a question, why we should talk about such a trivial, seems like a trivial density matrix we should talk about, why we should talk about that? Because another very simple property of this density matrix is that this density matrix short-range correlated in the sense that if we are talking about trace rho ZZ as a 2-point correlator of the poly Z operator, which is the charged operator of the Ising symmetry, you can see that this 2-point correlator is 0. So there is no true long-range correlation of this density matrix. Okay, we should talk about that. Let's go back to the GHZ state again. And as I told you before, one of the elegant property of GHZ state is a long-range correlation of the ZZ correlation function. And you can interpret this long-range correlation as the similarity between the cast state itself and the final state by applying 2 poly Z operators. We can show you this. We can understand this long-range correlation by 2 steps. For example, let's start from a cast state and apply a single Z operator to the cast state. The resulting state by applying a single Z operator is orthogonal to the initial state. But the dramatic thing gonna happen if we apply if we further apply another poly Z operator to the intermediate state to get a final state, let's say ZZ psi. And you can see that the ZZ, and by this process, we drive the intermediate state back to the original form by applying another Z. And it's not sensitive to the distance between I and G. That is, even I and G are well separated. These 2 steps are still well defined. And that is, we can deform a initial state to an intermediate state, which is very different from the original state. And then we take one more step and then drive this state back to the original form. That implies a very long-range correlation between these 2 Z operators. Then let's consider the 1 plus X as a density matrix. As I said before, if we only apply the ZIZJ at one side of the density matrix become very different. But what about we conjugate the poly Z operators? Let's still consider 2 steps. Let's conjugate the density matrix by a single poly Z operator, let's say ZI. And you can test that the rho and the ZI rho ZI are actually orthogonal, in the sense that by conjugating ZI rho ZI, we deform the rho, which is in the charge even sector of the Ising symmetry, to the charge odd sector of the Ising symmetry. You can see that because of the strong symmetry, we can define charge sector to the density matrix. For example, 1 plus X is in the charge even sector in the sense that every single state within this density matrix should have an even charge of the Ising symmetry. And by conjugating a Zi, the result, the intermediate density matrix is actually the charge in the charge odd sector. But the dramatic thing happens if we further conjugate another poly Z operator Zj, and the resulting density matrix, let's say the final state is Zij rho Zij, is actually in the charge even sector and actually come back to the original form. So although the traditional two-point correlator show you a very short-range correlation behavior, there is still a very subtle correlation, low-range correlation between Zi and Zj in the sense that if we conjugate the density matrix by poly Z operator, the similar dramatic thing gonna happen as an analog to the pure state. Yes. So how to quantitatively describe this dramatic similarity between the rho and the Zi rho Zj? Let's learn from the quantum information scientists. A very typical similarity measure between two density matrices is the fidelity between them. So the hidden long-range correlation of such kind of density matrix, let's say 1 plus x, is measured by the so-called fidelity correlator of the charge operator. For example, for the poly Z operator is actually the charge operator of the Ising symmetry. So with the help of the quantum information science, let me give you a formal definition as aka the water parameter of the strong two-weak SSB in the sense that in the sense of the fidelity correlator. Let's say we say the density matrix rho with a strong symmetry has the strong two-weak SSB if the following fidelity correlator is of the order 1, despite how long x and y are separated. And here OX and OY are local operator carrying the local charge of the strong symmetry G. Okay, and why you may ask me a question, why is a strong two-weak spontaneous symmetry breaking? Let me show you why is that. Because the traditional two-point correlator, let's say trace rho OO, is short range. These emphasize that this weak symmetry is not broken spontaneously. So the spontaneous symmetry breaking of the corresponding states we're talking about is actually the strong two-weak spontaneous symmetry breaking. Okay. Oh, you may grill me that here that, whoa, I recognize that you find a phenomenon rather than a phase-on matter, because if you are when you talk about the phase-on matter, you should define the universality. That is the stability of the states within the phase against some kind of robust or against some kind of symmetric perturbation, aka the robustness of the states against the symmetric perturbation. For example, for the cast state, the stability of cast state is emphasized that we can never find a strongly symmetric local unitary operator to deform the cast state to a symmetric state. In the sense that if we apply U to a cast state, the resulting state should always be a Z2 spontaneous symmetry breaking state. That is the stability of the SSB for pure state. As an analog, in our work, we provide a stability theorem for the strong two-weak SSB in the sense that if we have a density matrix with a strong symmetry G has a strong two-weak SSB in the sense of a low-range fidelity correlator, and we further consider strongly symmetric finite depth local quantum channel E, let's say E, then the resulting state by channeling the density matrix by this channel, the final state E rho should also have a strong two-weak SSB. It means that you can never destroy a strong two-weak SSB by any symmetric perturbation. That is the stability of the strong two-weak SSB. With the help of the stability theorem, we can unambiguously say that, well, we find a well-defined phase-on matter in open quantum system. Yeah, so that's why we should introduce the fidelity correlator as the order parameter of the strong two-weak SSB, because we tried some other maybe equivalent order parameters, but we failed to prove this stability theorem. Only fidelity correlator can give us the stability of the strong two-weak SSB. That's the importance why we should introduce the fidelity correlator. as the universal order parameter. That universal is pretty important. Okay, let me show you a very simple example of the Ising model under decoherence. Let's consider the 2D Ising paramagnet with the following Hamiltonian, actually the sum over the minus x over the whole system. You can easily to see that this system has a very strong Z2 symmetry. And let's consider nearest neighbor ZZ decoherence. That with the explicit form of the channel, I'll show you at the left-hand side. And here Zi and Zj should be nearest neighbor side. And Z here is the poly Z operator. And we can show you that for P equals to 0, we start from a product state. And for P equals to 1/2, the final state is actually exactly the 1 plus x. So, and furthermore, we find a transition between these two different states. One is a symmetric state, one is a strong two-weak SSB. And the PC is which is approximately 0.109. And the phase transition. And we proved that by map to a StatMech model, we proved that the universality class of such kind of decoherence-induced phase transition is actually fall into the universality class of 2D classical random bound Ising model along the Nishimura line. And the fidelity correlator is actually the correlation function of the random bound Ising model along the Nishimura line. And you may ask me a question. You have a phase diagram. You have two different phases. And as you said in the very beginning of your talk, you see that every single pair of two density matrices should be two-way connected if they fall into the same phase. And in our work, we show that if rho 1 and rho 2 fall into the same phase, either symmetric or same phase, they are actually two-way connected. The one way is pretty simple. That, for example, let's see in the phase diagram rho 1 and rho 2. Let's the dynamics of driving the rho 1 to rho 2 is pretty simple. That we just further apply the ZZ defacing channel. It's pretty simple. And the other way that's a recovery channel is simply use the path recovery map, which is quasi-local and log depth, and it's actually two-way connectivity between two density matrices. But we can show that if rho 1 and rho 2 are separated by the phase transition critical point, we can never find a reverse channel that bring the rho 2 back to the overrun form, because the path recovery map failed to recover such kind of dynamics because of the non-locality. Okay. Okay, after show you a very simple example, you maybe have a more further question that, well, I recognize that you find a phase of matter which is universal in open quantum system, but why you should call it a spontaneous symmetry breaking? I didn't see the spontaneity of your phase. That's a very good question. Let me answer you. Let's recall the spontaneity of the pure state SSB. Let's consider, as I said before, the cast state is the symmetric property of the cast state is pretty fragile in the sense that although the cast state is symmetric, under an infinitesimal local perturbation, even in the thermodynamic limit, the symmetry property, the global symmetry, going to be completely destroyed to either all up or all down, which are all in asymmetric. And well, the different symmetry vacuum depends on the sign of the external magnetic field. So that is spontaneity of the SSB. And for the mixed state, let's say the 1 plus x again, the spontaneity property is similar in the sense that even in the thermodynamic limit, let's consider 1 plus x. Let's trace out only one side, let's say I. The final state is literally the maximally mixed state without a fixing charge sector, aka it's a just identity. So this operation emphasizes that the symmetric property of the strong two-weak SSB is still so fragile in the sense that a local perturbation can lead to global change of the whole system. And you can easily to understand that any global change can never be recovered by any local operations. So in our previous work, we proved a theorem of spontaneity in the sense that if with density matrix has a strong two-weak SSB, then we always have a symmetry breaking local quantum channel, let's say EI, that can never be locally recovered by another local channel EI total. In the sense that for the strong to weak SSB, it seems symmetric, but this symmetry property is so fragile that can be destroyed, globally destroyed by some local symmetry breaking perturbation. And you know that this global change can never be restored by any local operation. Thus, irrecoverability emphasizes that the density matrix we're considering are actually spontaneous symmetry breaking. The spontaneity is unambiguously captured by the spontaneity theorem. Okay, these two properties pretty important, but you may ask me a further question. If for the pure state, the spontaneity can be quantitatively captured by a divergent dynamical susceptibility. So if you wonder if there is similar properties for the open quantum system, can we quantitatively describe the spontaneity of the strong to weak SSB? Of course we can. Let's move to the second part of today's talk, that is fluctuation dissipation theorem in the open quantum system. And in particular, I will give you a quantitative description of the spontaneity of the strong to weak SSB. Well, let's recall the spontaneity again for the pure state, which is captured by a divergent susceptibility quantitatively as a derivative of the magnetization with respect to the external perturbation. Okay, let's consider the 1 plus x as the simplest example of strong to weak SSB, and consider a single Z defacing channel. You can see that here is the single Z operator, and you know that this kind of quantum channel breaks the strong symmetry to weak symmetry because you can see that the cross operator Z is not commutative with the Ising symmetry. So this channel is only weakly symmetric. And under this channel, in particular for P equals to 1/2, the resulting density matrix is identity rather than 1 plus x. So the spontaneity is captured by the following quantity. That is actually the derivative of such a quantity with respect to the intensity of the external channel perturbation. You can see that the intensity of the channel perturbation is exactly captured by the probability P here. And you may ask what kind of F here it is. What is it? What is it? It's actually some kind of fidelity between the rho and the density matrix conjugate by the charged operator. A single charged operator. It's not a fidelity correlator. It's actually some kind of fidelity average of the charged operator. It's pretty much like an analog to the local order parameter of the pure state SSB. Okay. And in particular, if we choose rho as the pure state, it's exactly the local order parameter. Okay. And you can see that for the initial state rho, which is strongly symmetric, because of the strong symmetry, the fidelity between rho and 0Z is exactly 0. But under the symmetry breaking perturbation, the final state E rho is no longer strongly symmetric. It's only weakly symmetric. The weak symmetry means that the perturbation screw the different charge sector to each other. So for the final state, if we calculate the fidelity average of the poly Z operator here, it's actually non-zero. Of course, because it's only weakly symmetric. Let's see the fidelity average of the charge operator is the fidelity magnetization as the analog of the magnetization for pure state. And the corresponding derivative of the magnetic fidelity magnetization with respect to the intensity of the external perturbation is actually the generalized susceptibility. Let's say it's a fidelity susceptibility. So for the simplest case of the Ising symmetry as a strong to weak SSB, the spontaneity is quantitatively captured by the divergence of the fidelity susceptibility. That's pretty interesting. It's as a perfect analog of the pure state SSB. Okay, for more generic case, let's consider a strong symmetry G with a corresponding charge operator O, I, O, J, etc. And the spontaneity can be quantitatively captured by the fidelity susceptibility with the formal definition here against the external charge, the local charge defacing channel. Here, the probability P reflects the intensity of this kind of symmetry breaking channel. And the derivative of the magnetic magnetization with respect to the probability is the formal definition of the fidelity susceptibility as the generalization of the susceptibility to the open quantum system. And you may ask me, where is the fluctuation dissipation theorem? You know that for the pure state or thermal state, the linear response theory tell you that the dynamic susceptibility is very closely related to the correlation behavior to the of the system through the fluctuation dissipation theorem. It's actually the fluctuation dissipation theorem for the pure state or thermal state is actually the dynamic susceptibility is actually the average of the 2-point correlator over the whole system size. So for the you may wonder if there are similar properties for the open quantum system. Here it is. At the first line of the bottom part of this slide is actually the formal representation of the analytical representation of the fidelity susceptibility. It looks pretty much like a fidelity correlator. But the drastic thing is that the sum over the different positions of local charge operator is inside the fidelity. And the even more drastic thing is that the fidelity is a very highly nonlinear quantity. It's a quantum information theoretic quantity. It's highly nonlinear. So if we just take the sum sign outside the comma, outside the fidelity, it's actually not an equality, it's an inequality because of the concavity of the fidelity. So we can, if we naively take out the sum outside the fidelity, we can only get the lower bound of the fidelity. But fortunately, by some very elegant calculations, we can conclude that although we can never find a equality between the fidelity susceptibility and the fidelity correlator over the whole system size, we can always find that the fidelity susceptibility can simultaneously be bounded, both upper bounded and lower bounded by the average of the fidelity correlation over the correlator over the whole system size. You can see that the lower bound is the sum of the fidelity correlator over the whole system size, and the upper bound is actually the square of the sum of the square root fidelity over the whole system size. Okay, the square root of the fidelity is pretty simple. That we just take a global square root of the fidelity quantity. It's pretty simple. It's not a square root inside; it's a square root outside. So it's pretty simple. And the square root procedure here doesn't change the qualitative behavior of the fidelity correlator. That is, if the fidelity correlator is order 1, so does the square root of fidelity correlator. And that's pretty simple. And with the fluctuation dissipation theorem, we are ready to analyze the different scaling behavior of the susceptibility in different mixed state quantum phases. Okay, for the spontaneous symmetry breaking phase, we can although we cannot calculate the exact quantity of the fidelity susceptibility, but with the help of both lower bound and upper bound, and further by the analytic representation form of the fidelity susceptibility, we can unambiguously conclude that in the spontaneous symmetry breaking phase in the open quantum system, the corresponding fidelity susceptibility divergence in the thermodynamic limit. Specifically, its scaling behavior with the system size is order n, linearly scale with the system size. So the scaling behavior is unambiguously determined. And similarly, for the symmetric short-range correlated state, the fidelity susceptibility is order 1. Although we can never calculate the exact quantity of the susceptibility, and the short-range correlated phase give you a order 1 susceptibility. So if we can design an experiment If we find, well, a density matrix has a order 1 susceptibility, then we can tell you that it is a symmetric phase. And the critical point or phase between them can either be order 1 or divergent, but the divergence should be sublinearly. It cannot divergent in the linear sense. It should be slower. The divergence at the critical point should be slower than the linear scaling. Okay. Oh yeah, okay, you may ask, for the pure state, this dynamic susceptibility can be really easy to be proved but experimentally. For example, the magnetic susceptibility can be easily to be proved by some kind of, for example, the NMR or neutron scattering, etc. But what about the fidelity susceptibility? The even drastic thing here is that if you really want to experimentally measure the fidelity, which is highly nonlinear quantum information theoretic quantity, it's generally required the quantum state tomography. The desperate fact is that if somebody tell you, well, let's do this quantum state tomography, it basically means that, oh, let's just give up. But unfortunately, we have although we can never precisely probe the fidelity susceptibility, we can still estimate it in a very reliable way. And we can, in our second paper with Chen He and Yichen, we provide a very polynomial proxy of the fidelity susceptibility that serve a convergent lower bound of the fidelity susceptibility. And even more important thing is that every single term in this polynomial proxy is actually only a polynomial of the density matrix rho. So if some quantity is only a polynomial of the density matrix, let's call the Renyi 2n correlator. It's only a polynomial of the density matrix. It can actually be measured by classical shadow tomography rather than the quantum state tomography, whose complexity is much lower than the quantum state tomography. Okay, the classical shadow tomography is actually the procedure of composed by the random unitary and the local randomized measurements. This very elegant experimental idea is proposed by the Yuan-Hao and etc. And every single term in our polynomial proxy can be measured by this classical shadow tomography, in the sense that we can only perform the randomized measurement near the local operator rho OI and OJ, because we only care about the correlation behavior near the I and J, and we don't care about all the information away from the I and J. So this kind of procedure significantly reduce the complexity of the experimental measures. And by this measurement, we can reliably estimate the different scaling behaviors of different mixed state quantum phases. For example, the spontaneous symmetry breaking, the symmetric short-range correlated, and the critical point or phase in between them. Okay, let me summarize my today's talk. Firstly, I gave the formal definition of the strong to weak SSB, as well as the universal order parameter that is called the fidelity correlator. And by tell you the universal behavior by the stability theorem and the spontaneity property by the spontaneity theorem, we unambiguously determine that the strong to weak SSB is a well-defined mixed state phase of quantum matter, and it is the spontaneous symmetry breaking. And to quantitatively capture the scaling behavior of the spontaneity, we propose a fluctuation dissipation theorem with in the open quantum system, and unambiguously determine the scaling behavior of different phase of matter in the open quantum system of the fidelity susceptibility, although we can never calculate that. Okay, there are several further applications of strong to weak SSB. First application of strong to weak SSB is a higher form symmetry. With these wonderful guys, we conclude that the mixed state topological order can be comprehended as a strong to weak SSB of a higher form symmetry. These are Caroline Zhang from Harvard University. Yichen and Cengke and Zhang has been introduced at the very beginning, and Zhu Xiluo is a new faculty member in Georgia Tech. And secondly, as we know that for the pure state or thermal state, if we consider the spontaneous symmetry breaking of some kind of continuum symmetry, there is a Goldstone mode, which is gapless. And you may ask me if there is an analog property for the strong to weak SSB. Here it is. With Xiaoyang Huang, Marvin Chi, and Andy Lucas, we conclude that for U1 strong to weak SSB, the emergent diffusive hydrodynamics as a low energy emergent hydrodynamics of the U1 symmetric system, the diffusive hydrodynamics is exactly the Goldstone mode of the U1 strong to weak SSB. We use the Schwinger-Keldysh field theory as the path integral of the Lembladian master equation. And the diffusive hydrodynamics can be captured by the low energy equation motion of the Schwinger-Keldysh field theory. Okay. And furthermore, another application of the strong to weak SSB is in the quantum state preparation. As everybody knows that if we really want to prepare a symmetry protected topological state from a trivial product state, we should break the symmetry locally. At least locally breaks the symmetry. Otherwise, we can never do this because of the stability of the SPD state. But if you guys are familiar with the chemistry, we know that plenty of chemical reactions can never happen without the help of catalyst. So the catalyst is pretty important to participate in the chemical reaction. And finally, after the chemical reaction, the catalyst keeps invariant. So as an analog to the chemistry, we introduce the concept of many-body catalysts that prepare a SPT state from a trivial product state by a purely symmetric quantum circuit. It seems impossible, but it happened in our paper with David, Stephen, and Rahul Nandkishore. And in particular, we see that a strong to weak SSB is a very ideal catalyst to prepare the SPT state from a trivial product state to SPT state. And the whole state preparation procedure leaves the catalyst invariant. Okay, that's all my today's talk. Thanks for your attention.
All right, thank Jian-Hao for the nice talk. And is there any question from the audience? Actually, I have a question. Is there something in analogy to the Goldstone mode that one can probe when you have any type of strong to weak SSB for continuous symmetry?
Yes, I think you can prove that by some kind of transport experiment. You know, at very long time, the diffusive hydrodynamics is comprehended as a damping of the superfluid. But from the perspective of the strong to weak symmetry breaking, if we strictly forbid the SSB of weak symmetry, there is only diffusive hydrodynamics, and it can easily to be proved by the transport experiments.
I see. So it's diffusive. And then if we think about a case like I have a higher form U1 symmetry or higher form continuous symmetry breaking in thermal equilibrium, then we know there's still something Goldstone mode with a spin 1 vector boson correspond to that. And for that Goldstone boson, it's very robust in the sense that even I weakly break the strong 1 form symmetry for U1 or any continuous symmetry, that a gapless Goldstone mode can still exist. And I wonder if you have something like strong to weak higher form symmetry breaking, but that's for continuous symmetry breaking, do you still have any, but you weakly break the 1 form symmetry, do you still have any signature as it was unbroken?
Well, quite frankly, we don't know. That's a very interesting question, and it's definitely gonna be a very exciting further direction of the strong to weak SSB. But quite frankly, honestly, we don't know the answer. But I have to acknowledge you that it's a very exciting question. I'm happy to consider further on your question.
Right, thank you. Any other question? If no question, I think we are running just hitting the time, and let's thank Jian-Hao again.
Thank you.
Right, thank you.